Okay, so we're going to continue with conductors, dielectrics and boundary condition. So this is conductors. Most metals belong to this group. So conductivity is a measure of how easily electron can travel through material under the influence of external electric field, or F external. So a perfect conductor is a material with conductivity is equal to infinity. So this is the most ideal situation. So the conductivity of most metal is in the range from 10 to the power of 6 to 10 to the power of 7 Siemens per meter. Conductivity of a material would depend on several factors, which include temperature and also the presence of impurities. So these are the examples of conductors. So the first one, we have silver with a conductivity of 6.2 times 10 to the power of 7 Siemens per meter, followed by copper with 5.8 times 10 to the power of 7. So usually we use copper in most cases, okay, because copper is much more cheaper compared to silver. And then followed by gold, aluminium, iron, mercury, and finally carbon. A conductor has a large number of loosely attached electrons in the outermost shells of the atoms and migrate easily from one atom to another in the presence of an external electric field. So under usual condition, if you don't have any external electric field, so the loose electrons move in random direction and varying speed. Their random motion produces zero average current through the conductor. When an external electric field is applied, the electrons move in an average velocity called the electron drift velocity, which gives rise to a conduction current. So this electron drift velocity in a conductor, when an external electric field is applied, will give you equal to minus mu E, which is electron mobility, times with the electric field. So this electron velocity is in the meter per second. Okay, so in the case of semiconductors, current is contributed by the movement of both electron and holes. So in conductors, you only have electrons, but in semiconductors, you have electrons and another one, we call it as holes. Okay, so the hole drift velocity, okay, UH, is given by mu H, which is hole mobility, times with the electric field. And the unit would be meter per second as well. The total conduction current density due to the movement of electrons or electrons and holes, so whether you have only electrons, so electrons only would refer to the conductors, and when you have electrons and holes, that would refer to semiconductors. Okay. So in the end, the total conduction current density J would be equal to conductivity of the electric field, conductivity of the materials, which is in Siemens per meter, okay, times with the electric field for both conductors and also semiconductors. So sigma here is the conductivity in Siemens per meter. In a perfect dielectric, the permittivity should be equal to 0. So this is dielectric, yeah, the opposite of conductor. Okay, so conductivity would be equal to 0. So when this conductivity is 0, so your J would be equal to 0. But in a perfect conductor, so the conductivity should be equal to infinity, as high as possible. So when you have the conductivity equals to infinity, your E would be equal to 0. Okay, so a perfect conductor is an equipotential medium, meaning that the electric potential is the same at every point of the conductor. For a dielectric, okay, it is the opposite of conductors. The electrons are tightly held to the atoms, so much that it is very difficult to detach them, even under the influence of an electric field. So here, consequently, no current flows to the material at all. Alright, so a perfect dielectric is a material with conductivity is equal to 0. So usually for dielectrics, the conductivity range from 10 the power of minus 10 to 10 the power of minus 17. Okay, so these are very good insulators, we call it, the other name for dielectric. So ideal dielectrics do not contain free charges. The atoms in these dielectrics have electrons that are tightly bound to the nuclei, which is the opposite of conductors, because the electrons can jump here and there. An external electric field, E external, does not affect mass migration of charges in a dielectric, okay, but it can polarize the atoms or the molecules in the material by distorting the center of the cloud and the location of the nucleus. So what it can do, if you have these external forces going around, the electron cloud surrounding the nucleus in an atom will be distorted, creating an electric dipole. So it only changes the polarization. So this electric dipole will induce an electric field called the polarization field, which is in the opposite direction of E external. The presence of the electric dipoles alter the relation between electric field E and electric flux density D. So when you have D, the flux is equal to permittivity of the electric field E. So what it does here, the dipoles, you plus P at the end. So P here, if it is directly proportional to E, the medium is said to be linear. And if the P is in the same direction of the electric field, we will call the medium as isotropic. Next, what is dielectric breakdown? So when we subject a dielectric to a strong electric field, okay, the keyword here is strong electric field, some of the electrons will be removed from the nuclei. So when this happens, sparking can occur and the dielectric material can sustain permanent damage. So this phenomenon is known as the dielectric breakdown. So that's why it is important for us to identify the dielectric strength, okay, which is the minimum electric field intensity at which the dielectric breakdown would occur. So for example, if it depends on the material. So you have air, petroleum oil over here, polystyrene, glass, and mica. So let us see the relative permittivity. So permittivity refers to E. So R is the relative permittivity. So air will have a relative permittivity of 1. Okay, and the dielectric strength here is 3. So you shouldn't go beyond that to avoid dielectric breakdown. So for example, if you're using a dielectric of glass, so relative permittivity is 4.5 up until 10. Okay, depends on the glass that you have chosen. So the dielectric strength for glasses is typically between 25 to 40. So when you use glass as your dielectric, make sure that it doesn't go beyond the dielectric strength, okay, in order to prevent dielectric breakdown. Okay, finally we have the boundary condition. So it is a condition that the field, which is both electric and magnetic, must satisfy at the interface separating two different media. So when you are considering two different materials here, it is important to study the behavior of the electromagnetic wave, okay, the EM field, through different media, because usually we will use more than only one media, okay. Boundary conditions specify how the tangential and normal components of the field in one medium are related to the components of the field across the boundary in another medium. Okay, let us jump into the figure over here. So when you are considering two different materials, okay, you will have different permittivity, different conductivity, and different permeability. Alright, so it will have its own E, sigma, and also mu. So when you are considering these two materials, okay, you will have its own normal component, its own tangential component, and its own field, E or D. Like this one. So usually there are two kinds of component that we're going to consider here. So the first one is tangential. Okay, tangential is the one that is going horizontally of the material. And second one is the normal component, which is going vertically through the material. So the tangential component of the electric field E is continuous across the boundary between any two media. Okay, so tangential component is the one that is going horizontally. Okay, so that's why the electric field is continuous across the boundary. For normal component, okay, of electric flux D, changes abruptly at a charge boundary between the two media, and the amount of change is equal to the surface charge density. Okay, so the normal component is the one that goes vertically across the two materials. So this is the boundary condition for the electric field. So consider medium 1 and also medium 2. So here we have the field components. You have tangential E and tangential D, normal E and normal D. Okay, so the general form for any two media, we will have E1T is equal to E2T. So E is the tangential E of medium 1, okay, is equal to tangential E of medium 2, so E2T. Alright, okay, and then we have tangential D, okay, so you have D1T over permittivity 1, which is equal to D2T over permittivity 2. So D1 here refers to medium 1, 2 here refers to medium 2. And then for normal E and normal D, for medium 1 and medium 2, you will have permittivity of 1, E1N, minus permittivity of 2, E2N, which is equal to rho S. So rho S here is the surface charge density at the boundary. And for normal D, you'll have D1N minus D2N, which is equal to the rho s, the surface charge density. Now, if you consider the first case, medium 1 is a dielectric and medium 2 is a perfect conductor, which is usually the general case in most cases. Okay, we would consider different mediums here. So you have medium 1 dielectric, and of course medium 2 would be the conductor. Okay, so this is an ideal case because you have perfect conductor. Okay, when you have perfect conductor, meaning that your conductivity is equal to infinity, so your E would be equal to 0 as well as your D everywhere in the conductor. So when you have E and D is equal to 0, okay, so your E1T and E2T now is equal to 0. Okay, and then your D1T over permittivity 1, D2T over permittivity 2 will also equal to 0. Okay, referring to these two tables before. So E and D is equal to 0, okay, because it is perfect conductor. Okay, since your medium 2 is a perfect conductor, okay, your E2 is equal to 0. So how do you find out your normal E and normal D now? So E2 and D2 would be equal to 0. So you just have to cross those two. And this would leave you with permittivity 1, E1N is equal to rho S. And for normal D, you have D1N is equal to rho S. Okay, so electric conductor boundary. For the previous example, we have E to T is equal to 0. So this gives E1T equals to 0 as well. So you don't have tangential E already. So tangential E would be equal to 0. And then for E2, just now, because it is perfect conductor, the medium 2 is equal to 0. So now you can find out what E1N is. So E1S is equal to rho S over permittivity of material 1. Okay. So at conductor surface, okay, this will be equal to, so E1 is equal to rho S over permittivity of 1 n hat. So n hat here is a unit vector directed normally outward from the conducting surface. Okay, this is the updated table where you have medium 2 is the perfect conductor. Okay, so medium 1 you have the dielectric E1, and then medium 2 you have it a perfect conductor where E and D is equal to 0 everywhere. So you have E1T is equal to E2T equals to 0. D1T equals to D2T equals to 0 because your medium 2, okay, medium 2 is equal to 0, which make everything equal to 0. So the only thing that you have to find out is the normal E of material 1, okay, medium 1, and also the normal D of medium 1. Okay, so this will leave you with E1N is equal to rho S over permittivity of 1, and D1N is equal to rho S. So rho S here refers to the surface charge density. Okay, but if you have a condition where both medium, okay, medium 1 and medium 2 is actually not perfect conductor, so none of these are perfect conductors, so you have to use the table, the one in the middle here, okay, where you are considering dielectric 1 and also dielectric 2. So the electric field here, E1T is equal to E2T, so you have to find out using the long equation, all right? So in a conducting media, E gives rise to the current densities where J is equal to conductivity of the electric field. So you have to find out this one. So E is actually equals to J over the conductivity. So that's why you have J over conductivity at medium 1, which is equal to J over conductivity at medium 2, and so on. So in electrostatic field, J1n is equal to J2n, which would give J1t over conductivity at medium 1 equals to J2t over the conductivity at medium 2. So this applied for all electrostatic field.